All right, let's dive right into this explainer and reveal the invisible mechanics that govern literally every single movement of energy in our universe. Welcome back. Today, we're tearing down the walls of our everyday perception to really understand heat and thermodynamics.
So, think about this for a second. Why does a hot cup of tea always cool down, but a cold room is never going to spontaneously heat it back up? I mean, it's a simple, everyday observation, right? But it actually points to this massive core mystery regarding the natural, irreversible flow of the universe seeking balance. Energy is on a one-way street, constantly moving from a state of order toward disorder. And that observation brings us straight to thermodynamics. Simply put, it's the study of energy in transit. It's the invisible dance of tiny atoms and molecules happening all around us. Thermodynamics proves that energy cannot be created and it can't be destroyed. It can only be transformed. And that one profound principle is actively powering everything in existence, from the microscopic cells in your own body right up to massive airplane engines cruising across the sky. So here's our roadmap today. We're covering 1. The invisible energy dance. 2. Thermodynamics in daily life. 3. The core universal laws. 4. Heat transfer and measurement. And 5. Powering the future. We're going to start by observing simple everyday actions before we uncover the hardcore mathematical formulas and high-stakes applications that govern them all. Okay, part 1. The invisible energy dance. Let's peel back the curtain on reality for a minute. Think about the last time you wrapped your hands around a warm cup of cocoa on a freezing cold day. You aren't just magically feeling heat, you're physically experiencing a microscopic dance of energy transfer. The rapid vibrations of the molecules in that mug are actively crashing into the molecules of your skin, transferring their kinetic energy directly to you. And your brain? It interprets those billions of tiny microscopic collisions as warmth. Moving on to part 2. Thermodynamics in daily life. This perfectly illustrates how these grand scientific principles are happening right inside your kitchen. Energy is literally constantly surrounding us and in motion. Look at your refrigerator. It's essentially stealing heat from inside its compartments and pumping it out into your kitchen to keep your food fresh. When you sweat after a workout, your body is using the latent heat of vaporization to cool you down. Or when you lock the lid on a pressure cooker, you're trapping steam to raise the boiling point of water well over 100 degrees Celsius so your dinner cooks faster. Even Earth's atmosphere acts as a massive thermodynamic system trapping greenhouse gases. You're navigating these exact principles every single day. All right, part 3, the core universal laws. Let's see how all of this builds into the absolute rules that nature places on energy. We have to begin with the somewhat oddly named 0th law of thermodynamics. It states that if systems A and B are in thermal equilibrium with system C, well, then they're in equilibrium with each other. Now, why does that matter? The crucial point is that this law guarantees a room temperature thermometer placed in a glass of ice water will accurately reflect the liquid's temperature once they balance out. Without this law, thermometers would be completely useless. Next up is the first law, which is energy conservation. The steps are pretty straightforward. Supply heat to a system, increase its internal energy, and do external work. Think about it. When you use a hand pump to inflate a football, or when you're at the gym and your body turns the chemical energy from your food into weightlifting power and body heat, you are actively executing the formula delta Q equals delta U plus delta W. You are quite literally a walking thermodynamics equation. Have you ever noticed those intentional gaps left between railway tracks? They're there for an absolutely crucial reason. Thermal expansion dictates that materials grow when heated. If civil engineers don't mathematically account for this linear expansion, those tracks expand in the summer heat with nowhere to go. They buckle, which causes devastating train accidents. Physics really doesn't care about convenience. The math just has to be respected. Now, imagine walking on the beach. You've got scorching hot sand burning your bare feet right next to cool, refreshing ocean water. This brings us to specific heat capacity. It explains perfectly why the beach sand and the ocean receive the exact same amount of intense sun energy all day long, yet reach vastly different temperatures. It all comes down to how much thermal energy a specific substance needs to actually warm up. And that leads us to an incredibly important number, 4184 joules per kilogram Kelvin. That is the massive, specific heat capacity of water. Because water requires so much energy just to raise its temperature by a single degree, it serves as an extraordinary natural coolant. It's the exact reason we use it to regulate everything from heavy industrial factory machinery to your very own car's engine. Part 4. Heat transfer and measurement. Now that we understand the laws, let's explore exactly how this thermal energy jumps around.
According to Newton's law of cooling, a boiling hot cup of tea at 0 minutes experiences a rapid loss of heat by minute 5. But by 20 minutes, the cooling rate has slowed down significantly, and at 45 minutes, it finally hits thermal equilibrium with the room. Basically, the rate of heat loss is proportional to the temperature difference. And here's a rather dark but fascinating application for you. Forensic scientists actually use this proportional rate of cooling to estimate a time of death based on a body's temperature.
These advanced heat mechanisms are everywhere. Conduction is why you stir hot soup with a wooden spoon instead of a metal one that would burn your hand. Radiation explains how the sun's energy crosses the freezing, absolute vacuum of space to keep Earth warm. And adiabatic processes, they allow automotive engineers to design diesel engines that compress air so incredibly fast it ignites fuel without even needing a spark plug.
Okay, consider this. Spilling 100-degree liquid water on your hand versus getting hit with 100-degree steam. My question to you is, why is the steam burn so much more severe, often causing terrible damage, even though the temperature of the liquid and the gas is exactly the same?
While the answer lies in a huge number, 2,260 kilojoules per kilogram. That is the massive extra latent heat carried by steam. Steam carries this hidden heat because immense energy was required to change its state from liquid to gas. It's kind of similar to how ice cubes will stubbornly stay at 0 degrees while absorbing heat to melt in your drink. When that 100-degree steam hits your skin, it releases all of that extra hidden heat as it condenses back into water, making the burn vastly worse.
Which leads us to the ultimate constraint in physics, the second law and entropy. There is no perpetual motion machine. Because heat cannot spontaneously flow from cold to hot without external work, just like your AC unit requires electricity from the grid to actually cool a room, the Carnot efficiency limit proves that a perpetual motion machine is completely impossible. The universe demands its tax, always in the form of entropy.
And finally, Part 5, Powering the Future. Let's talk about why mastering these principles changes everything.
First off, for the students tuning in, here is your immediate payoff. Acing highly competitive exams like IIT JEE, NEET, and BITSAT requires mastering calorimetry and the kinetic theory of gases. In these exams, thermodynamics often serves as the ultimate scoring section. Why? Because once you grasp these fundamental physical constraints, the math stops being just abstract memorization and follows a perfectly logical, predictable path.
But look, it goes way beyond exams. Green energy, mechanical engineering, climate science, EV battery cooling, advanced carbon capture. These formulas aren't just for passing tests, guys. They are the exact blueprints that engineers and scientists are using right now to shift the world towards sustainable green technology. Designing a better electric vehicle literally means designing a better thermodynamic cooling system.
So a final question I want to leave you with today. Will mastering these ancient laws of thermodynamics be your key to solving our modern global energy crisis? You now have the foundational tools to understand and innovate tomorrow's high-tech industries. So how will you harness the invisible dance of energy? Keep that in mind the next time you sit back and watch a hot cup of tea slowly cool down. Thanks for joining me on this explainer.